Hello dear students, today we will be continuing with our chapter Electrostats and today's topic of discussion is Coulomb's law. So as in the last class we have studied about charges and the basic properties of charges. Among that we have one property of charge that like charges repel each other while unlike charges attract each other. So the amount of attraction or repulsion between the charges was given by the scientist Coulomb, and the expression was given as force is directly proportional to the charge on the two bodies. Let us say charge on first body be Q1 and second body be Q2, and it is also proportional to the inversely related to the square of distance between them. So the final expression we have is kq1 q2 upon r square. So this is the magnitude of force of attraction or repulsion between the two charges, which is quite analogous to what we have studied in class 11th, force of gravitation, which was g m1 m2 upon r square. So here the value of k is 1 by 4 pi epsilon naught, where epsilon naught we are saying if we are calculating in vacuum, and its value is 9 into 10 raised to power 9 Newton meter square per Coulomb square. So if we change the medium, then we'll be writing epsilon equals to epsilon naught epsilon r, where epsilon naught is the absolute electric permittivity and epsilon r is the relative permittivity. So this epsilon naught value is 8.85 into 10 raised to power minus 12 Coulomb square Newton inverse meter inverse square. So this is the value of epsilon naught. So we can see from here that this electrostatic force is medium dependent. While this gravitation force was independent of medium. So this is the major difference between the two forces. And also another difference is that electrostatic force experiences both repulsive as well as attractive nature, while gravitational force experience only attractive nature. So this Coulomb scientist first gave the expression, and his experiment was torsional balance experiment, which he performed to find the amount of force between the charges. So how he performed, let me give you overview. So he took the glass jar and he suspended a body in such a way, and another body, let me say it body A and B. Initially both are neutral. So, and he placed a strip of measurement tape at the inner surface of the jar in order to have the proper measurement. So initially when both the bodies were uncharged, no deflection was observed between the bodies. But when this body A was removed from here and it was charged, we have seen in our last class the ways of charging of the body. So we have seen either by rubbing, by induction, and by conduction. So these three methods we have seen to charge a body. So this body A was taken out of the charge jar and it was charged, and again it was suspended in the jar. So what happened is, now a deflection was observed and in the rope or the fiber which was used. So it was seen the force between the two charges will be equal to the rotation or the angle of twist of the fiber. So this, we can say that restoring force is proportional to the angle theta. So we can say that the amount of rotation is equal to k theta, and it is also Rf, right? So we can calculate the value of force from here. That will be torque upon R from equation 2, and substituting the value of equation 1 here, we get this expression. So from here he calculated the Coulomb's force expression, which was finally F equals to K Q1 Q2 upon R square. So this is the magnitude of the force, but we know that force is a vector quantity. So if we have to write the vector form of Coulomb's law, so the vector form of Coulomb's law is like this. If we take the two charged bodies, let it be Q1 and Q2, and the distance between them is R. So this force is, as we have said, that it is central force, that is, it acts along the center of the line joining the two charges. So on body 2 we'll see that force will be F21, force on 2 due to 1, while on first body it will be F12. So our expression will go like, if we write for the first body, force on 1 due to 2, we'll be writing magnitude and R1 minus R2. So this is the magnitude, and here we'll be writing direction. So how we have to write direction here? Direction of this charge is towards left. So as we know that direction of any vector quantity is given by vector upon its magnitude. So we'll be writing it as vector will be R1 minus R2 vector upon R1 minus R2 mod. Here it is square. Since if we see the direction towards right side, then it will be given as final minus initial r2 minus r1 vector, while in the left side it will be given as r1 vector minus r2 vector. So we are seeing for the first body and the direction is towards left, therefore we have considered r1 minus r2, right? So we'll be substituting it here and we get force on 1 due to 2 is k q1 q2 upon r1 minus r2 cube, and here r1 minus r2 vector. So this is the vector form of Coulomb's law. Next we will study about the principle of superposition. So what this principle says that suppose we have two charges q1, more than two charges q1, q2, q3 and so on. So net force on any charge will be, let's say we have to calculate force on 1. Net force on 1 will be force on 1 due to second charge plus force on 1 due to third charge. So we can say that the net force experienced by any charge, either it will be 1, 2, 3 or nth charge, that will be vector sum of the forces acting on it due to the rest of charges of the group. So the net force is the vector sum of forces acting on it due to all other charges. So this is the principle of superposition. So while having the discussion of the Coulomb's law, we have considered every time the charges and as the point charges. So we can say that the limitation of Coulomb's law is it is applicable only for point charges, point size charges. So point charges doesn't mean that the size of the charges of the point size. We can also consider it from the frame of reference. Suppose we have a charged body and we are seeing from the very far distance. So from the far distance we'll consider this body as a point charge. So this is one of the limitation of the Coulomb's law, and for the continuous charged bodies we'll study further how to calculate the force in that. Now let's solve a question. The question says a charge q is divided into two parts such that when these two parts are kept at the same separation, the electrostatic force between them is maximum. So there was a charge q and it is divided into two parts. Let us say that q charge is divided into x and q minus x. So it is divided into two parts. Now it is said that when these two parts are kept at the same separation, so some separation, it should be some separation here. So let us say that this charge x and q minus x are kept at some separation r. So it is said that the electrostatic force between them is maximum. So we have to find the charge on each part. So first of all we can find electrostatic force, as we know that electrostatic force will be equal to k q1 charge q1. So the first body has the charge x while the second body has the charge q minus x, and the distance between them is r. Okay, so we have given that the force is maximum. So whenever we have to find maximum or minimum value, for that we differentiate. So here we'll be differentiating the force df by dx equal to 0 in order to find the maximum value of the force. So let's differentiate it. We'll getting kqx minus k x square upon r square. So differentiate this, df by dx equals to kq minus 2kx by r square equals to 0. So it will become kq equals to 2kx and x will be equal to q by 2. So the charge on the first body is x, that is q by 2, and the second body is q minus x, which is again q by 2, and we have to find this charge on the each body, which we have done. So we'll continue in our next lecture the further topics. Till then, keep learning. Thank you.